Problem F7-2. Determine the normal force, shear force, and moment at point C. So, on this beam, we have two applied forces, this 10 kilonewton downward force on the right-hand side, and a 30 kilonewton meter applied moment at the left-hand side. We also have some reaction forces. There's a reaction force at A, which we can see the reaction at, or the support at A is a roller support, so the reaction is purely in the vertical direction. And a reaction at B, we can see that B is a pin support, so it will create both a vertical and a horizontal reaction. And at this point in time, we do not know the magnitude of those reactions. So we need to find that first. To find those, we do Newton's second law on the beam as a whole. In the x direction, there is just the x component of the reaction at B. So RBx equals 0. In the y direction, we have reaction at A, which we're going to assume is upward, reaction B, which we're going to assume is upward, and this 10 kilonewton force applied downward. We do have this 30 kilonewton meter moment here, but that does not actually apply any net force. Remember, this moment is probably in the form of a force couple, which have a net force of 0. So when looking at moment, we should pick a point of our choosing. I selected point A, and we find all the moments about point A. So this 30 kilonewton meters is applied. It doesn't matter that it's located 1.5 meters to the left of point A. This is an applied moment. It does not matter where it is. It is just 30 kilonewton meters. The reaction at A will not create any moment about point A. The reaction at B is upward, and it's applied to the right of point A, so that'll create a counterclockwise rotation, which by our sign convention is positive. So it's 3 meters away, so 3 meters times reaction at B. And this 10 kilonewton force is downward and to the right of A, so it will create a clockwise rotation, which in our sign convention is negative moment. It's 4.5 meters away, so it is 4.5 meters times 10 kilonewtons. So with these two equations, our solutions for reaction at A and reaction at B are 5 kilonewtons each. Next, the question is determine the normal force, shear force, and moment at point C. So what we're going to need to do here is cut this beam in half at point C and select one of the two segments to look at. I have opted to select segment A. So sum of forces, there is, again, this 30 kilonewton meter moment does not apply any net force. So we have the assumed upward reaction at A. We also have the shear at C, which, looking at our sign convention, a positive shear applies a downward force on the right-hand side. So reaction at A minus the shear at C equals 0. Next, sum of moments equation. I have again opted to find the moments about point A. So there is again this 30 kilonewton meter applied moment here. Again, it doesn't matter where it's applied. The reaction at A will not create any moment. The shear at C will create moment. Even though it's shear, not necessarily moment, it is still a force applied away from our center of rotation. So again, shear by convention, positive shear is downward, and that will create a clockwise rotation, which our sign convention says is negative. So negative 1.5 meters times the shear of C. I did that here. And lastly, there will be an internal moment at C. Going back to our sign convention for moment is that on the right-hand side, it's a counterclockwise moment. So on the right-hand side, it's positive. So the sum of moments equation about point A becomes 30 kilonewton meters, this applied moment, plus the internal moment at C minus 1.5 meters times the internal shear at C equals 0. We solved for that. We already had that Ra was equal to 5 kilonewtons, which means that that the shear at C is 5 kilonewtons. And then once we have that, we know everything but the internal moment at C. We can solve that the internal moment at C is negative 22.5 kilonewton meters. And lastly, the question also asked, what is the normal force? There are no horizontal forces. Remember, the reaction at B is 0. So there is no normal, or as we've been calling it, tension force in it. Normal at C is 0.